Hey everyone, and welcome back to another explainer session. I am your host, and today we're stepping into the clinic to diagnose a massive topic from the Cambridge AS level physics syllabus, specifically paper 9702. We're talking about wave mechanics. Look, we all know waves act as nature's ultimate energy carriers, right? But the way examiners test this can be incredibly tricky. Whether you are looking at the vastness of space or literally just tossing a pebble into a pond, the underlying mathematical mechanics dictate exactly how energy moves through our universe. It's a brilliant, completely invisible system, and my goal today is to make sure you see the world around you and your next exam paper in a completely different light. Let's get right into it.
So, the absolute foundational concept you need to grasp here is the idea of progressive waves. A progressive wave transfers energy from one place to another, but, and this is absolutely crucial, it does not transfer matter. I really want you to think about that for a second. Whether it's the sound of my voice reaching your ears right now, the light from a distant star hitting a telescope, or just ripples spreading out on a pond, these progressive waves are moving pure energy across space. The actual physical matter, the air molecules in your room, the water drops in that pond, they essentially stay right where they started. They just oscillate back and forth about their equilibrium position. They are the delivery mechanism, not the package itself.
All right, we have a highly structured journey ahead to secure those top marks. We're starting from the basic building blocks with the anatomy of waves, then hitting the core wave equations, moving into transverse versus longitudinal waves, exploring the Doppler effect, unpacking electromagnetic waves, and finally tackling the mind-bending phenomena of polarization and light. Let's start with Section 1, the anatomy of waves. Before we can solve complex wave interactions, we've got to build our vocabulary. Okay, pay close attention to this, because what's really interesting here is how this highlights a massive classic exam trap. Look closely at these two graphs showing wave motion. At first glance, they look totally identical, don't they? But check your axes carefully. Seriously, whenever you see a wave graph, check the x-axis first. The top graph measures displacement against time, which gives us the wave's period. That's the time it takes for one complete oscillation. But the bottom graph, it measures displacement against distance or position along the wave, and that gives us the wavelength. It is incredibly easy to confuse the two under pressure, so always check to see if you are tracking the wave's progress over a span of seconds or over a physical span of meters. Let's formally define our terminology to build up our toolkit. First, amplitude. This tells us the maximum displacement of a particle from its resting or equilibrium position. Basically, how tall is the wave? Then we have period, which is the time it takes for one complete oscillation. Frequency is simply the number of complete oscillations per second, and we measure that in hertz. Remember, 1 hertz equals 1 full vibration per second. And finally, wavelength. This is the actual physical distance between two successive points on the wave that are vibrating exactly in phase.
Which perfectly brings us to the concept of being in phase or out of phase. As you move along a progressive wave, the vibrating particles are often slightly out of step with each other. Look at points P and R on this displacement distance graph. They are at the exact same peak of the wave, meaning they are perfectly in phase, separated by 360 degrees, or exactly 1 full wavelength. But now compare point P to point Q. Point P is sitting at a peak, while point Q is all the way down at a trough. They are 180 degrees out of phase, or exactly in what we call antiphase. Phase difference is really just a precise mathematical way to measure this exact fraction of a cycle between oscillating particles. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Awesome. Let's jump into Section 2, core wave equations. We've got the anatomy down, so let's look at the mathematical mechanics of measuring power. If waves are essentially energy carriers, kind of like wind carrying energy across a vast ocean, only to crash onto a distant shore, we naturally need to ask, how can we precisely quantify the intensity of that delivery? Well, the math gives us a really striking rule, and examiners love to test this relationship. Intensity is defined as the transmitted power per unit area, and the crucial takeaway here is that intensity is proportional to the amplitude squared. Listen, this is not a simple one-to-one linear relationship. Because it's squared, even small drops in wave height drastically cut the power. For example, if the amplitude of a wave is halved, the intensity doesn't just halve, it actually drops by a factor of 4. Understanding the square law relationship is absolutely essential, whether you're designing sound systems or calculating the immense brightness of distant stars. Moving on to Section 3, transverse versus longitudinal waves.
Because not all waves move matter in the exact same way. When energy travels, the particles it interacts with can oscillate in one of two directions relative to the flow of that energy. In transverse waves, the particles vibrate at right angles, so perpendicular to the direction of energy transfer. But in longitudinal waves, like a sound wave traveling through the air, the particles vibrate back and forth parallel to the direction of energy transfer. And it's this parallel movement that causes the particles to bunch up into tight areas called compressions and then spread out into sparse areas called rarefactions. This graphic perfectly illustrates the physical comparison between the two. Think of a transverse wave as taking a long rope and shaking your hand up and down. The wave itself moves forward horizontally, but the rope is just moving vertically. A longitudinal wave, on the other hand, is like pushing a sudden pulse directly down a coiled slinky spring. The coils compress and stretch horizontally, moving back and forth in the exact same plane that the energy is traveling. Now, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @aceexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's escalate the complexity for Section 4, the Doppler effect. What actually happens when the source of a wave starts moving? I want you to imagine the pitch of a police siren as the car speeds towards you and then as it zooms past. The pitch sounds higher on approach, right? And then it drops noticeably as it drives away. This is the Doppler effect in action. Look at the moving source on the right side of this image. Notice how the circular wavefronts actually bunch up closer together in front of the moving object? Because the source is literally chasing its own waves, the wavelength gets shorter. This results in a higher frequency, which our ears interpret as a higher pitch. Behind the source, the waves are stretched further apart, giving us a longer wavelength and a lower frequency. Now, what's truly mind-blowing is that the Doppler effect isn't just for police sirens. It applies to all waves, including light. And this principle is literally the evidence that proves our universe is expanding. When astronomers look at electromagnetic radiation from distant galaxies, they see a decrease in the frequencies, something we call redshift. The fainter the galaxy, the greater the shift is, which suggests that the further away a galaxy is, the faster it is moving away from Earth. It's wild to think that the macroscopic literal expansion of the entire universe is understood entirely through the microscopic behavior of waves. Which is the perfect bridge to Section 5, electromagnetic waves. Let's look at this special type of transverse wave that can miraculously travel through the sheer vacuum of space. So, unlike mechanical waves that need a physical medium, like a rope or water or air to travel through, electromagnetic waves are transmitted by variations in electric and magnetic fields oscillating at right angles to each other. This table from the syllabus maps out the entire continuous electromagnetic spectrum. We go from extremely high-energy gamma rays caused by atomic decay, down through X-rays, ultraviolet, visible light, infrared, microwaves, and all the way to massive radio waves used for telecommunications. Keep in mind, there are no sharp boundaries here. The properties simply change as the wavelength gradually increases across the spectrum. But no matter where they sit on that massive spectrum, whether they are tiny, incredibly dangerous gamma rays or giant radio waves spanning kilometers, all these waves share one incredible fundamental property when they are in a vacuum. They all travel at the exact same universal speed limit, the speed of light. That is 3.00 times 10 to the power of 8 meters per second. Finally, we reach our climax in Section 6, polarization and light. This is where we learn how to filter reality. You see, most light sources, like the sun or a standard light bulb, produce what we call unpolarized light. This means the electric and magnetic fields are oscillating in multiple random planes all at once. But because electromagnetic waves are strictly transverse, we can filter them. Passing that chaotic light through a specific plastic polarizing filter forces the oscillations into a single uniform plane. The wave is now plane polarized. Here's the real trick, though. If you take that now polarized light and try to pass it through a second filter that is rotated perpendicularly to the first, we call it a crossed filter, it will block the remaining light entirely. This image brilliantly illustrates that exact phenomenon. You can visually see how unpolarized light hitting that first vertical grid gets sliced, so only the vertical oscillations survive. Then, when that vertical wave hits the horizontal grid of the second crossed filter, absolutely nothing can get through. The transmitted light drops to zero. Oh, and here is a top-tier exam tip. This is a property exclusive to transverse waves. Longitudinal waves, like sound,
vibrate parallel to travel, so they physically cannot be polarized. If an exam asks you to prove a wave is transverse, polarization is your absolute go-to answer.
Of course, in the real world, it's not always just all or nothing. As you rotate that second filter, the transmitted intensity gradually changes. For everything in between 100% transmission and 0%, we use Malice's law. The formula states that the transmitted intensity equals the initial intensity multiplied by the cosine squared of the angle between the two filters. This elegant equation lets us calculate exactly how much power survives as we twist the lens. It's the exact science behind things like LCD screens and the polarized sunglasses you wear to reduce glare.
We've covered a massive amount of ground today, from the basic anatomy of wavelength and frequency right up through the Doppler effect and Malice's law. So from the polarized 3D glasses you wear in a movie theater to the red-shifted light of ancient galaxies expanding into the void, I leave you to wonder how much of our reality is fundamentally dictated by these invisible mathematical careers of energy. Think about that the next time you turn on a radio, look up at a star, or just toss a pebble into a pond. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.